Hello everyone, this is Dr. Tasadduq Hussain and we are studying the wave mechanical concept of atom. In our last lecture, I discussed about the Louis de Broglie dual nature of matter, and in today's class, we are going to study about the Heisenberg's uncertainty principle. This lecture will be divided into 4 different parts. First, we will go through the introduction, then derivation of the equation of Heisenberg. Then we will look at the experimental verifications of the equation of Heisenberg. And finally, we will conclude our lecture with the significance that the Heisenberg's uncertainty principle has. Now, moving towards the introduction part of the Heisenberg's uncertainty principle. Before having the introduction, we should know that there was one of the experiments that is called as Young's double slit experiment that basically explained the concept of diffraction. In case of Young's double slit experiment, what happens is we shoot electrons or we shoot light from one of the single slits having a distance or a width of d to a screen here, and in the screen what we see is there are dark and bright regions. We call it as the dark fringe and the bright fringe. In case of bright fringe, what happens is we see there is a constructive interference, whereas in case of dark fringe we see that there is destructive interference. Now, when an electron comes from this slit having a width of d, the change in the momentum of the electron on the x-axis is very less or negligible. That's why we can detect this electron somewhere here. However, this electron can go through a process of diffraction because electron is also acts as a wave. So if we can say that this electron is somewhere here also, but there is going to be some uncertainty in the position or in the position of this electron on the y-axis, that we will represent with delta py, whereas the change in the momentum towards the x-axis will be represented by delta px, and the change will be represented with an angle theta. In that case, in this bright spot, what will happen is there is going to be constructive interference. This constructive interference can be represented in the form of an equation d sine theta is equal to n times lambda, and this is always the bright spot or the bright fringe. However, in case of the destructive interference, wherein the waves cut each other, in case of this dark spot, the equation is going to be d sine theta is equal to half of this wavelength, because this wavelength from here to here is half, and this is the other half. Now, from this equation 1, what I can say, we can first write this is the dark fringe. From this equation, now I can say that sine theta is equal to lambda by d. The sine theta is equal to lambda by d or n lambda by d. From de Broglie's equation, we know that this lambda is equal to h by px, or the momentum and the wavelength, they are inversely related with each other. In case of this equation or this image that I have shown here, you can see that delta px is a straight line. That means the change in the momentum of the electron as it hits through the slit is very less here. So we can say that delta px is very small or negligible. The change in momentum on the x-axis is very negligible. In that case, what I can say, I can represent this theta by a very small angle for the screen. So if I suppose that the screen is very far away from this slit, in that case this theta is going to be very small. So if I consider that situation, then theta sine theta is equal to the theta, which is a very small angle. At that point of time, this theta is going to be equal to lambda by d. So I can represent this equation as theta is equal to n lambda by d. which can be equal to delta y by px. Now since the change is very small, I can represent this delta px as px, means that there is very less change in this px. Now in order to see how Heisenberg arrived at the uncertainty principle, if we consider the same slit, single slit, or the Young's experiment, in that case we'll consider the case 1 and case 2. In case 1, what we'll do is we'll make this slit very small, very narrow slit, and in another case we'll make the slit very big. In case of narrow slit, when you see it on the screen, you will see this bright fringe is very broad. This bright fringe is very broad. However, in case of the big slit, you will see that there is a localized spot, or this wavelength that you are seeing here, it's very less. Okay, so in this case what's happening is, in the case 1, there's more diffraction. Because the diffraction is more, that's why we're seeing a very big wavelength. However, in the second case, the diffraction is very less, and because of that we are seeing very less diffraction. Okay, now in this case what happens is, in case 1, when the electrons are hitting this screen, we'll see that we are more certain about the position of the electron going through this slit. Why? Because this slit is very small and we can exactly tell where the electron is. However, when it hits the screen, we can see that we are more uncertain about its momentum, because the momentum is getting more spread out. It can be from here, 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 here. So at one point of time, you can have the exact position of an electron or a photon that is hitting here, while as the momentum, you will be less certain in case of the momentum. On the other side, when the slit is very big, in that case what happens is, you are never certain about the position of the electron in this slit or position of the photon in this slit. However, now since you have got very less diffraction here, you can be more certain about the position or about the momentum of the electron or photon. So this clearly says that at one point of time we can have more certainty about only one of the things. Either we can be more certain about the position, or we can be more certain about the momentum. It's only because of this problem that Heisenberg was able to deduce the concept of the uncertainty principle. Moving to the derivation part of the Heisenberg's uncertainty principle, classical mechanics says that we can at one point of time know both the position as well as the momentum of a particle. However, Werner Heisenberg, who was a German physicist, in 1927 put forward the uncertainty principle, which is a consequence of the dual behavior of matter, which was put forward by de Broglie. We also know that light has dual behavior. According to Heisenberg's uncertainty principle, it's impossible to determine simultaneously both the position and the momentum of an object with certainty. It acquires significance when this principle is applied to elementary particles. This law means that if an attempt is made to measure the momentum, which is represented by P, of an electron with higher accuracy, our knowledge about the other, that is its position, becomes less accurate, and vice versa. Mathematically, it can be stated that if delta x is uncertainty in position of the object and delta p is uncertainty in case of the momentum of this particle, then the product of these two uncertainties is always equal to a constant that can be equal or greater than h by 4 pi. So in simpler terms, if I put this equation, that simply means the product of the uncertainty in the momentum and the product of the uncertainty in position is always going to be greater or equal to h by 4 pi. This equation here is the Heisenberg's uncertainty principle. In real terms, how he arrived at this conclusion was that the product of uncertainty in the position and momentum is always equal to h cross by 2, where h cross is called as the reduced Planck's constant or Darrow's constant. Since this h cross is always equal to h by 2 pi, if we replace this h cross with h by 2 pi in this equation, so if this is equation 1 and this is equation 2, if I replace the value of Dialog's constant in the Heisenberg's uncertainty principle, then I will get the product of uncertainty in position and momentum of an electron is always going to be equal to h by 2 pi. So I replace this h cross with h by 2 pi into 1 by 2, or in other words it's going to be h by 4 pi. And then when you solve this equation, you will arrive at this conclusion. This delta p is the change in the momentum, and since we know that momentum is always equal to mass into velocity, so for delta p it becomes mass into velocity. Mass is going to be constant and velocity is changing. So actually delta p is equal to m delta v. Upon substituting the value of delta p in this equation, we can get that m delta v is multiplied with delta x is greater or equal to h by 4 pi. Or in other words, if we put the uncertainties on one side, we can say delta v into delta x is greater or equal to h by m 4 pi. Delta v into delta x is greater or equal to h by 4 pi m. So this equation is also Heisenberg's uncertainty principle. So what this equation means is that the position and velocity of an object cannot be simultaneously known with certainty. Heisenberg's derivation can also be written in terms of proportionality, wherein we can say that the delta p is actually greater or equal to 1 by delta x, since h by 4 pi is a constant value. When delta p is very small, the momentum of an object can be measured accurately, but uncertainty will be introduced in its position and vice versa. In a similar manner, when delta x is 0, the position can be located with accuracy, whereas delta p becomes infinity. So if delta x is 0, then delta p becomes infinity. That means the momentum cannot be measured. However, for most of the practical purposes, you have to take this equation as delta p into delta x is always greater or equal to h by 4 pi. That concludes our derivation part. In order to look at the experimental verification of the Heisenberg's uncertainty principle, delta p into delta x greater or equal to h by 4 pi, let's consider an electron E moving in a circular path, this circular path. When this electron collides a photon of light of wavelength, for example 1 angstrom, the photon transfers some of its energy, because it has high energy, to the electron itself, and hence the electron changes its path. That's the electron does not move along the circular path, or which is the expected path of the electron, but along a changed path as shown here in this changed path. Due to the changed path, the velocity of an electron is also changed. So in this changed path, the velocity is also changed. Hence, in other words, we can say the determination of the exact velocity of the electron becomes impossible, because you know the exact location of the electron. Although the measurement of the position or the location of an electron is certain, since it can be observed by kind of means of a microscope. On the other hand, if we see that the electron is collided with a photon of light of wavelength greater than 1 angstrom, so when it's collided with 1 angstrom or greater than 1 angstrom, so if we collide it with greater than 1 angstrom, the photon has a low energy in that case and is not able to change the circular path of the electron, and hence the velocity of an electron is not changed. Thus the determination of the exact velocity of electron is possible, but the position or location of the electron cannot be determined accurately. In other words, we see that the exact determination of the position and velocity, or which we also call as momentum, of the electron cannot be made simultaneously. Moving towards the significance part of the Heisenberg's uncertainty principle, we know that the uncertainty principle is more significant in case of the microscopic objects. However, for the macroscopic objects, its significance is not that much. Now, in order to clarify this issue, what we can do is we can take an example wherein we will take a very heavier object and we will take an electron and then see how much difference is in there, what we call as the position and the momentum. Now, for example, if I have a ball that has a weight of around 200 grams, it's a macroscopic object, and then if I have an electron whose mass I know is equal to 9.11 into 10 to the power minus 31 kg, 9.11 into 10 to the power minus 31 kg. So in both the cases we know the mass. Now if I consider that the uncertainty in position, that is delta x, for both of them is 5 picometer. So in this case it's 5 picometer, and in this case also delta x is 5 picometer. Let's calculate the uncertainty in the velocity. According to Heisenberg's principle, we know that delta x into delta p is equal to h by 4 pi. Now if I put in the values of h and the 4 pi and then the mass of an electron or the mass of this ball, what will happen is, in the first case, for the case of ball, we'll get the values 5 picometer, that is uncertainty in the position, multiplied by the, since delta p is equal to m delta v. Now m we know in case of this case is 200 gram, into delta v is equal to h by 4 pi. So h by 4 pi is 6.626 into 10 to the power minus 34 joule second, divided by the value of 4 pi, that is 4 into 3.14. Upon solving this equation, I'll get value of delta v is equal to around approximately 5.275 into 10 to the power minus 23 meter per second. So this is the uncertainty in velocity for a 200 gram ball having a uncertainty in the position as 5 picometer. Now again calculating it for an electron, what we'll consider is the uncertainty in the position is same, that's 5 picometer, into the mass of an electron, that's 9.11 into 10 to the power minus 31 kg, into the uncertainty in the velocity that we have to calculate, will be again equal to the same value. And upon calculating delta v, it will be equal to 1.158 into 10 to the power 7 meter per second. In this case, in case of an electron, when I am calculating it for the hydrogen atom for the first orbit, or for an electron which is in the first orbit, we know from Bohr's equation that the electron in the first orbit has a velocity of around 2.18 into 10 to the power 6 meter per second. Now when we calculated the uncertainty in the velocity, we see that it is 1.158, so there's a lot of difference between these two values. So this clearly indicates that at one point of time we can be more certain about the momentum or about the position of a particle. The value of uncertainty in case of velocity that we calculated for the ball shows that this value is small and negligible in comparison to the velocity with which an object of this size is moving. This means that for microscopic objects or for the bigger objects that we have, both the position and velocity can have precise values, or in other words, the uncertainties in the position and velocity are very small. So the uncertainties in the position and the velocity both, or what we call as momentum, are small. And hence both of them can be simultaneously determined up to a reasonable extent. So both of them we can determine in case of the microscopic objects. However, in case of the electron, what happens is the value of the uncertainty in velocity indicates that this value is greater than the velocity of an electron in the first orbit, which I already mentioned here. This means that for subatomic microscopic moving particles, like for electrons, protons, or for very small particles which are moving in a circular path, both the position and velocity cannot have the precise values. So here either position or the velocity is going to have precise values. So if you have a precise value in this, then there is no precise value in this, and if you have precise value for velocity, you are not going to have precise value for the position of an electron. And in other words, we can say that both of them cannot be determined with accuracy at one point of time. So overall, this discussion clearly shows that the Heisenberg's uncertainty principle has no significance for the macroscopic objects, while as it's a very important consequence when we deal with the atomic or the subatomic particles like electrons and protons. In case of significance, when we compare the Bohr's atomic model and the Heisenberg's uncertainty principle, the Heisenberg's uncertainty principle tells us that due to the wave nature of an electron, we cannot describe the exact path followed by an electron in an atom at any single point of time. Thus, Bohr's theory, according to which an electron are regarded as having a fixed position or an orbit, so this electron has a fixed position or an orbit of definite energy, is no longer correct. Then how can we describe the position of an electron in an atom when we take into consideration the Heisenberg's uncertainty principle? In order to describe its position in an atom, the maximum that we can do is that we, according to the Heisenberg's principle, can only predict the probability or the relative chance of finding or locating an electron with probable velocity in a particular region of space around the nucleus. So in a particular region around, this is a particular space wherein we can find the probability of an electron around the nucleus. So that means we can only predict where an electron is most likely to be found, or in other words, we cannot say where the electron is exactly located. We can only tell about the probable position where an electron can be found. In other words, we can say that the uncertainty principle rules out the possibility of strictly defined orbits for an electron which were suggested by Bohr. That pretty much concludes my lecture for the Heisenberg's uncertainty principle. I hope that you understood everything that I have shown in this class. If you like what we are doing here, then please subscribe and share our channel. Thank you for watching today's lecture. Take care.